Hi there, my name is Annie Moa, and today's date is May 25th, 2024. And today I will be going over the case connections for Unit 4. So I decided to take a look at Case 1. Just for the sake of time, I'm not going to read through the scenario, but the first question is discuss the normal mechanism of ammonia transfer in the body that should be occurring. And how is nitrogen transport connected to gluconeogenesis in the fastest state? So during the fastest state, proteins are broken down into amino acids that are subsequently released into the bloodstream. Alanine and glutamine are the two major amino acid carriers of nitrogen. In general, the carbon units of these amino acids are converted into glucose and ketone bodies to provide fuel for the body. The nitrogen units of these amino acids are converted to urea in the liver and excreted in urine by the kidneys. Transamination is the process of removing nitrogen from amino acids by enzymes called aminotransferase, and all these require pyridoxal phosphate as a cofactor. For instance, here, aspartate aminotransferase is responsible for transferring the nitrogen or amino group of aspartate or amino acid to alpha ketoglutarate or keto acid. The addition of the nitrogen group to alpha ketoglutarate will convert it to glutamine, and aspartate will then be converted to oxaloacetate. In peripheral tissues, such as our skeletal muscles, glutamate is generated through a similar process of transamination as previously discussed. Glutamate cannot easily be transported. It can be toxic if it's released into the bloodstream. So in order to safely transport ammonia to the liver, the enzyme glutamine synthetase is used to combine or fix glutamate with ammonia to form glutamine, a non-toxic carrier of ammonia. This reaction does require ATP. Glutamine is then released into the bloodstream, and once it reaches the liver, it can then be cleaved and deaminated by our enzyme glutaminase back into glutamate and ammonia. The free ammonia can then enter the urea cycle afterwards. Glutamate can be broken down even further in the liver through the process of oxidative deamination. Glutamate dehydrogenase is the primary enzyme responsible for this. In this reaction, the nitrogen unit of glutamate is released as ammonia, and the carbon units of glutamate reacts with water to yield alpha ketoglutarate. This reaction requires NAD or NADP as a cofactor. The ammonia produced in this reaction will be converted into urea also by the liver. As I previously mentioned, the carbon components of amino acids are used to make glucose and ketone bodies, particularly in gluconeogenesis. In the previous slides, I focused heavily on glutamine, but alanine is another important amino acid that is primarily transferred out of skeletal muscles into the bloodstream and then into the liver. So if you see in this diagram here, once it's in the liver, alanine undergoes transamination with alpha ketoglutarate, and this produces glutamate and pyruvate. I previously discussed how glutamate undergoes oxidative deamination, but what's important here is the pyruvate can actually undergo gluconeogenesis to produce glucose in the fastest state also. This glucose can be returned to the muscle or be transported to other tissues as a source of fuel. In the skeletal muscles, the glucose can be used in glycolysis and will produce pyruvate, which can then undergo transamination to generate alanine again. And then alanine can go back from the muscle tissues to the liver to restart this process. This is called the alanine glucose cycle, and this is where nitrogen transport is connected to gluconeogenesis. So moving forward in this case, further analysis show urine uric acid levels were elevated and there were normal plasma citrulline levels. What urea cycle enzyme is most likely deficient, and what urea cycle enzyme is least likely to be impaired? Which amino acid becomes essential, if any? In the case of this individual, she most likely has a deficiency of orthonine transcarbamylase, or OTC, which is right here. Normally, in the urea cycle, carbamoyl phosphate will react with orthonine to generate citrulline with the help of OTC. Afterwards, citrulline can proceed through the urea cycle, and ultimately the end product will be urea, which will be transported to the kidneys to be excreted, and orthonine can return to the mitochondria to be used in the urea cycle again. Carbamoyl phosphate can undergo an alternative pathway for pyrimidine synthesis. The enzyme carbamoyl phosphate synthase 2 uses carbamoyl phosphate to generate orotate, and orotate can then be used to make pyrimidine or it can be excreted in the urine. A defect in OTC would cause an accumulation of carbamoyl phosphate, which will be shunted to this alternative pathway. This would cause an accumulation of orotates, and high levels of orotate will be excreted in the urine, as evident in the case of this individual. Her urine uric acid was significantly high. Her plasma citrulline levels were normal, so that indicates that some molecules of carbamoyl phosphate are still used by OTC to produce citrulline. This means there is a deficiency of OTC, but is not completely absent. A OTC deficiency would cause arginine to become an essential amino acid. Besides being an important amino acid for urea and orthonine production, it also helps to maintain nitric oxide homeostasis. This is why intravenous arginine hydrochloride is used as a treatment for OTC deficiency. There could be a deficiency in the enzyme arginase, but this is less likely the cause. A deficiency in arginase would result in low levels of orthionine, which could impair OTC and cause carbamoyl phosphate to accumulate and enter the pyrimidine synthesis pathway, leading to elevated uric acid levels. However, we would also see high levels of arginine, but this information is not given to us. It is even less likely that the enzymes arginyl succinate synthase and arginyl lyase, which are right here and here, are deficient, because we would actually see high levels of citrulline in her blood, since these two enzymes are responsible for converting citrulline into arginyl succinate and subsequently into fumarate and arginine here. The carbamoyl phosphate synthase 1 is the least likely enzyme to be impaired, because a deficiency in this enzyme would significantly decrease the production of carbamoyl phosphate. Therefore, we would expect to see low urine uric acid levels, since little to no carbamoyl phosphate molecules will be used for the pyrimidine synthesis. So moving on to the next case, I chose case 3. So once again, just for time being, I'm not going to read the scenario, but the first question does ask, what is the best explanation for the presentation of gout in this individual? 1, overproduction of purines, 2, decreased salvage of purines, or 3, decreased urinary excretion of uric acid. So gout is a medical disorder characterized by painful inflammation in soft tissues and joints due to the accumulation of uric acid. Uric acid is the end product of the breakdown of purines like adenosine and guanosine in the liver. These nucleotides undergo a series of reactions as seen here that ends with the production of uric acid, which is then transported from the liver to the kidneys to be excreted. So a defect in purine salvage, such as a deficiency of the enzyme hypoxanthine guanine phosphoribosyltransferase, or HGPRT, also known as Lesch-Nyhan syndrome, will lead to decreased purine salvage, and subsequently more purines will be degraded to uric acid. Therefore, we should see an elevated level of uric acid being released in the blood and urine. Now, overproduction or increased purine synthesis can be due to diet or deficiencies that cause the accumulation of purine substrates. For example, in von Gert's disease, there is an accumulation of glucose 6-phosphate due to a deficiency of glucose 6-phosphatase. High amounts of glucose 6-phosphatase will be shunted to the pentose phosphate pathway, and this will lead to an increased production of ribose 5-phosphate, which is one of the substrates for purine synthesis. Increased purine production means that there will be increased purine degradation and elevated uric acid in the blood and urine. This individual's presentation is most consistent with decreased urinary excretion of uric acid. All three of these conditions will result in the elevation of plasma uric acid. However, as previously discussed, we would expect to see elevated uric acid in blood and urine in conditions that cause purine overproduction or decreased purine selfish. For this particular individual, his urinary uric acid level was significantly lower than the normal patient, which makes me believe that the primary root cause of his gout is due to the decreased urinary excretion of uric acid. This can be related to several causes, including acute or chronic kidney disease, acidosis, medications such as diuretics, hyperparathyroidism, and hypothyroidism. So to confirm if this individual's gout is truly due to decreased urinary uric acid excretion, he may require further blood testing, including a complete blood count, blood glucose, renal function lab tests, and thyroid function lab tests too. In addition, we may need to ask more information about his medical history, medication list, and diet. And speaking of diet, we have more information. Oh, here we go. Decreased urinary excretion of uric acid. That's the answer. So moving forward, he tells us that he recently switched from diet soda to regular soda because he read that the fake sugar diet soda was bad for him. He tells you he drinks about 4 and 5 liters of soda a day. What is the potential impact of this dietary modification on the presentation of gout? So high fructose intake is associated with elevated uric acid. Fructose metabolism is not highly regulated. Fructokinase has a very high Vmax, so this first step occurs really rapidly. Aldolase B has a low affinity for fructose 1-phosphate, so this second part of the reaction happens really slowly. So as a result of high fructose intake, the phosphorylation of fructose into fructose 1-phosphate by fructokinase occurs faster than aldolase B can cleave fructose 1-phosphate. This leads to the decreased amount of intracellular phosphate and ATP available, which will stimulate the degradation of AMP to adenosine monophosphate, or IMP. And this is done by the enzyme AMP deaminase. As a result, the rate of purine degradation increases, leading to increased production of uric acid. In addition, fructose stimulates the overproduction of purine and uric acid through amino acid precursors like glycine. There's also evidence that chronic high fructose intake inhibits renal excretion of uric acid. So this dietary modification done by this individual is likely contributing to his gout for sure. Thank you for listening to my presentation, and this is the end of it.